Hi friends, last session we have seen how to identify whether a problem is NP complete or not. In that we had said that L should be NP and L should be NP hard. That means all the problems in NP, if they are reduced to this problem, then this problem is called NP hard. And if this is a problem which can be verified in polynomial time, that means if this is in NP, then it becomes a NP complete. So what is the problem now is we need to check whether all NP problems can be reduced to this problem L. Now these are infinitely large number of problems we have, so it's not possible to work with infinitely large number of problems because these problems in the NP are almost infinitely large. Therefore, this is not possible. But yes, there is a way out that if we have some known so if we have some known problem which is already NP complete, and if this say LC, and if this problem LC can be reduced to our problem L in polynomial time, that means that our problem is at least as hard as the LC, which is NP complete problem. So if we can show this, then we can also say that L is NP complete. But the question is where to get this LC. Yeah, thanks to Cook's theorem, which was published in 1971, and this paper has proved that three-set problem is an NP complete problem. A three-set problem is basically a conjunctive normal form, a Boolean expression in a conjunctive normal form. That means it is and of clauses. So this is clause 1, this is clause 2, and clause 3, and so on. And each clause is a disjunctive of literals, that is or of the literals x1 or x2 bar or x3. That's one clause. Another clause x2 bar or x3 or x5. Another clause x2 or x5 or x7 bar, and so on. So this whole form phi equal to, so that's a conjunctive normal form, and here each clause has got three literals, exactly three literals. Therefore this is a three-sat problem where sat represents satisfiability. So here a three-set problem is given, and the aim is to identify the values of xi, whether they are 0 or 1, because we are talking of Boolean function. So xi is true or false. So each xi is true or false, so that phi is true. Yeah, definitely, because if there are n literals, then there will be 2 to the power n combinations, and hence solving this is an exponential problem. But of course, uh, lighter side of that is, if the values of xi are given by somebody, maybe magically if we know it, or somebody gives us the values of xi's, then we can just put them into this expression and identify whether each clause is satisfied or not. So if each clause is satisfied, then phi is satisfied. So for each clause to satisfy, one of the 3 literals have to be satisfied. So in all, if x1, x2, x3 values are given, whether they are true or false, then substituting into this, we can identify whether the value of phi is true or false. So this can be done in polynomial time. Therefore, this 3-set problem is NP problem, and Cook's theorem has proved in their paper in 1971 that it's also NP complete. So if we can prove that our problem can be reduced from 3-set problem, so our problem L, if we can reduce from the 3-set problem, then we can claim that L is at least as hard as 3-set problem. Therefore, we can say that L is NP complete. So friends, we got a shortcut in solving this problem. Instead of identifying all infinite problems available in the NP region and finding a way that each of these can be reduced to our problem in polynomial time, and then declaring that our problem is NP complete. Instead of that, if we could prove that a 3-set problem can be reduced to our problem, then we are sure that our problem is at least as hard as a 3-set problem. And because we know that 3-set problem is an NP complete problem, and hence our problem is also NP complete. So that's a simple logic we can use to declare whether a given problem is NP complete or not. So let's look into more examples in the coming sessions. So keep watching. Thank you.